Thank you for joining us. Good afternoon from the West Coast of the U.S. Welcome to the VIRL October webinar. And my name is Valerie Liu, and I'm the project manager here on the VIRL team. Getting on with some housekeeping items really quickly for this event. The webinar will be recorded as we usually do and made available after the webinar, as well as the Q&A transcript and everything you will be asking us in the chat section. So please make sure to utilize the Q&A section of this webinar to ask your questions. We have a team of experts here from the VIRL development and support team to help answer your questions. Well, if we do not get to them in time during the webinar, we will try to follow up with them and answer them when we post the Q&A transcript. And lastly, I just want to mention that we have 2 topics and an announcement in today's agenda, and we've had a few comments in the past of people saying that those webinars, sometimes they're a little bit too fast-paced or too many topics packed into one session. And the reason we do so is because we want to, really make this hour be worth your time and be efficient with our agenda. And personally, I have attended some webinars which are slower paced, and it's really just pretty hard for me to sit through it patiently. So we try to really make this a good use of your time. So, however, if the pace is still significantly faster and it's deterring you from absorbing any of the materials, do let us know in the feedback survey, which will pop up at the end when you exit the session, and we will take them into account for the future sessions. So here is a quick rundown of what we'll be covering today. We're going to take a deep dive on the live visualization feature, on its frameworks and capabilities. And Simon will be presenting the section, and he is our lead developer on the Autonetkit and Live Visualization features. And this is a great opportunity to ask Simon any questions you have on the session. And next up, we will have a sneak peek of a feature that's coming up in a new release on how to tweak your settings so you can overcommit some of your hardware resources, including CPU and RAM. And Tom Bryan, who is also a developer from our team, will be taking us through this demonstration. And at the end, we will have an exciting announcement that we'll be making for the first time to the public through this webinar. So stay with us till the end to hear it. And if you have a guess for what's going to come up, and you can comment that in the Q&A section of what you're guessing that we're going to announce. All right, so I will hand the ball over now to Simon, who will take us through the live visualization components. Simon, here you go. Simon, I think you're still muted if you're trying to talk.
Hear me now?
All right, here we go. Yeah, we can hear you now.
Okay, excellent. So I'm Simon Knight. I'm the lead developer working on the Autonetkit and the live visualization components of the VIRL platform. So today we're going to go in a deep dive. It's going to have a look through some of the architecture and layout of the live visualization system, and then I'll get a little bit into the features and a quick demonstration if we've got time at the end. So we're going to first just have a look at what the live visualization is, have a look at the client side, which is the bit that runs in the web browser, have a little bit of a look into how the server-side bit runs and how it collects all its data and sends that back, do a run through of some of the features that we've got in there today, and then do a quick demonstration. So in summary, what the live visualization framework is we're trying to make it a fast experimentation platform. So there's lots of things that you do once you've got a simulation up and running that is often a repetitive task, or you're ending up trying to write down, show commands on a bit of paper and trying to draw how all the bits fit together. So what we're trying to do is to automate that so that you can concentrate on experimenting with your network topology, whether that's for learning or whether that's mocking up a production network or something like that. So you're spending more of your time playing around with and carrying out what-if scenarios rather than trying to stitch how the network's actually working together. We also provide an interface to some of the running simulation controls. So some of the bits that you might run in the user workspace management, for instance, trying to give a visual heads-up view to that. We provide the ability to run commands on multiple devices, so a little bit like the tmux functionality, except here it's more of a static command. So if you're wanting to collect something like the route table from maybe 5, 10, 15 devices, depending on how big your network is, it becomes a lot easier to do that with one click rather than needing to log into each device and run the same thing manually. So trying to automate some of those repetitive commands. We also have an aggregated syslog, which is similar in a way in that we're sending everything back to a central point rather than needing to repeat or set those things up multiple times. And then some of the live topology views, which is collecting the routing protocols and showing how they fit together. So the motivation was really, in simplifying the common repeated tasks to make that quick and easy and get that out of the way, and trying to provide a graphical view of the status of the network and the controls to modify bits of that network. And that gives a more natural view of the topology than trying to do that through perhaps a table or a series of tables in something like the user workspace management. So that gives us some context to the commands we're running and the results that we're getting back, and then providing those routing topology views. And then some newer features that we've been experimenting with, such as running traceroute and plotting that visually, which works a lot nicer than trying to decode it from a series of IP addresses. So the requirements for the piece is that it runs in a web browser. We test extensively with Chrome, and Firefox and Safari work as well. Edge and Internet Explorer may work, probably won't work. It's the underlying core visualization code that we're using is similar to the Autonetkit configuration visualization piece. So if you've had issues with your browser there, then it probably will apply here. But in something like Chrome or Firefox or Safari, it should work well. Now, you don't need to have used Autonetkit to set up your OSPF or BGP or whatever routing protocols you're using. The only important thing is that you have out-of-band management access, so the management Ethernet interface that can get through from the LXC. So you need to have an LXC, management LXC running when you launch the topology, which is what we use to log into the devices and collect the information, and then the ability to be able to log into those devices. There's a nice tutorial up on YouTube that Joel put up the other week about the manual configuration, showing that you can have a configuration where he wrote all the IP addressing and all of the routing protocols by hand, and we can still use the live visualization as long as we can log into the device. So there's some more information on the YouTube channel in that video there. So in terms of getting to the live visualization piece, there's 3 ways you can get to it. One is by the simulations panel in VM Maestro. If you right-click on one of your simulations, one of the options there will be to launch the live visualization. Another way is through the user workspace management, which is the bit that sits on the server at port 19400 usually. And then when you go into simulation session there will be a button for live visualization. And you click that and that will launch it through. Or you can go directly to that. And so it's sitting on port 19402 and it'll just ask for your username and password. If you just put in your usual username and password that you would use for configuring in VM Maestro or configuring in the user workspace management, and then log in. And then that will present you with a list of the available session IDs for that user. And then you can select from there and it will flow through. So there's 3 methods to get them through. And as Valerie had said, we will put the slides up for here. So I'm going to go through reasonably quickly through the content of what we've got in the live visualization. And if you're interested in any specific slide, then please grab the slide deck or watch the video afterwards and then grab it from there. So in terms of the client-side piece, this is what's sitting on the browser. So it looks similar to the Autonetkit visualization because it is using the same layout engine. We're using NextUI, which is now actually an open source project accessible through DevNet for some of the base visualization. And then we've built a lot of bits on top of that for the interfaces and the grouping and the tooltips and things like that. So the very basic thing that we've got is the topology plotting. So we're getting the same X and Y coordinates and the node name and node subtype from the VIRL file. And then we're just rendering that on the screen. So this is showing what the topology that was launched was. and that gives us the information there. So even if you haven't got the LXC set up and the out-of-band management, you can still do some of the basic controls like viewing what the topology is and controlling the nodes and interfaces. But to do some of the advanced pieces which involve logging into a device and getting the information, that does require the out-of-band management access. So we've got the basic plot of the topology. I'm just going to run through some of the key elements that we've got in the user interface here, and then later on I'll run through the actual features that use those elements. So we've got the ability in the overlay menu to select one of the overlay graphs, and I'll show this right at the end of this piece, what the various overlays that we can use are. We've got some actions here, so this is running commands across the network and collecting various pieces and plotting various pieces. We've got the logs, so these are showing what's going on, whether a node status has changed or whether we've got a result from a collection command or whether we've sent a command across. So the log is really just giving a view of everything that we've tried to run or every piece of information that we've got back from the server. We have the syslog, which is what each device, if it's set up, will send it through to a central syslog piece, and then that will get forwarded through to the browser. So this is really showing us events as they occur across the network. And we can see even in this example here that we've got 3 devices right at the top, iOS v1, iOS v2, and iOS v3, and then a lot of events from 3 as I took links up and down. So you can see that we've got a heads-up view of multiple devices at once, which is really powerful to see the syslog aggregated into a single point. And having that directly with the topology can be quite powerful. We also have some basic topology information. So at the moment, this is really just showing the load on the server and the access coordinates to get to that management LXC. We could expand on this in the future. We have some information. So if you hover over a node, this one's actually the interface, or a node the other way around, then that will give you some basic information about that element. We have a interface popover. These labels are back to front. Interface popover gives us some context-specific actions relating to that interface. And then once again, back to front, the node popover here will give us some information and some actions that we can do with the node, so shutting it down or telnetting to the ports and things like that. And then if we've got a path, we can also hover over that to get a tooltip, which will give us some basic information. So they're really the basic elements that we've got in the live visualization user interface, and then the various features that I'll show later on in the slide deck, showing how we can use those basic elements to power the live visualization framework. So in terms of what's going on the server side, I'm just going to give a very quick overview. We've got the browser client, which is the bit that most people interact with that you'll see over on the left. We've got the web server bit, which does most of the commands, and then it interacts with some other pieces. So I'm just going to go through each of these piece by piece. So in terms of the browser client, that's the bit that runs in your web browser. It gives you the user interface to the system. This is really what most people only ever need to use. We have 2 methods of communication back to the server. So we have a series of REST commands that we're sending an action and expecting a response, or sending a command and hoping for a response, giving us some information on something like the node status, or sending a command through to the user workspace management and the VIRL core piece to do something like maybe shutting down a link or shutting down an interface and getting the response back. And then we also have a WebSocket feed, which is where we get the data that's being pushed from all the various components. So when something like a syslog message comes through, that will get sent through the WebSocket, or when we get a topology update, that will get sent through the WebSocket, or a traceroute update, for instance. So it's got 2 pieces there. The web server is really, as we can see from the diagram, got lots of things coming in and out. This is really the core piece that coordinates everything. So it's the bit that serves up the HTML and the JavaScript pages. So this is a thing sitting on port 19402. It's the endpoint for the REST services, and then it's also got the WebSocket connection. So this is really acting as like the multiplexer/router piece for all of the data that goes through. We've got the VIRL simulation engine, which is the VIRL core piece, which is really sitting at the heart of VIRL and what things like VMMaestro or the live visualization or user workspace management all talk to as the intermediate layer there. So this is the bit that we query it for topology information. So we're acting very similar to the user's workspace management, where it's got its status tables, where we query the simulation engine for information such as the topology state or the node and interface state, and then sending action commands such as asking for a node or an interface to be shut down or to be brought back up. So we've got the interface piece there from the web server. We've got the management LXC piece. So this is the bit that needs to be running to run a lot of the collection commands. So if you want to use the collection commands and the interface to the devices, the management LXC needs to be ticked when you launch the topology. And inside the management LXC piece, there's really 3 core components. We've got the ping piece. So this is doing periodically pinging each virtual machine on its management port. Once it starts responding to a ping on the management port, then that means that it's picked up the startup config that we've injected into it. So once we see a device responding to pings, we know that it's taken the config, which means it's ready to log in. Because if you've ever launched a topology, you'll see it go from building to active. But active just means that the virtual machine is ready for OpenStack. It doesn't necessarily mean that the iOS or iOS XR or NXOS or whatever device we're running, it doesn't mean that that device has actually taken the config that's running. That might be a minute, might be 5 minutes, might be 10 minutes, and that does vary depending on your processor load and how many machines you're starting up. So having the ability to ping and just to get a response back lets us know that once it starts responding, then we're good to log in. So it gives us a quick heads up view. Another function that the management LXC runs is to get the collection command, depending on what we've sent across from the front end, logs into each of the devices and runs the commands. It might be something like show IP route, or it might be trace route, or it might be getting something like the OSPF neighbors. It will run that command and then send that result onto the processor. And then the third thing that the management LXC does is sit as a syslog server aggregation point. So we can point each of the virtual machines and say, send your syslog messages to the LXC, and then it will forward it back through the web server down to the web browser over that WebSocket and to that view. So we can then get the messages straight away from a virtual machine showing up in our web browser. And then our running simulation, of course, is our virtual machines, which might be routers, it might be switches, it might be firewalls or servers or whatever are running. And these are the things that the LXC logs into, runs its commands, gets it back, and that also emit the syslog event. So I think everyone's fairly familiar with the actual simulation devices. The processor piece is the one that gets the information from the LXC once we've run a command, and it parses the output, so it turns the CLI output, if that's what we're running, into a structured piece of data, and then uses the inference engine that's based on Autonetkit. So if we see something like the OSPF neighbors command, we then parse that into some structured text, and then we'll use the Autonetkit engine to say, okay, I'm connected to this other router and this other router, so then I draw a link. And then from there, we can run that for each device in the network and build up a topology based on there. Once we've done the parsing and the inference, we'll send that to the live topology models piece, which is just storing what all those different overlay networks look like, and then it will send those models to the web server. And the live topology models is the final piece here, and that's really each of those topologies that we've inferred. So it might be OSPF, it might be BGP, or the physical topology. Once we've got all that collection data back, built up what the model looks like, we'll just store them here. So next time we can then update that when we get updated data from the device. And then that's sent back. So this is the overview. This is probably one that, if you are interested, grab the slide deck and have a look at, because there's quite a few moving parts, but that's really how they all fit together. So in terms of the features, we've got the actual overview topology here. So I've got a different topology shown. This is showing, I think it's 14 or 15 routers, so right at the personal edition limit. I just used all ISVs, but you can have a mix of different devices. We do support for all of the commands, all of the reference platforms that ship with VIRLs, NXOS and XR and things like that. So this is showing the overview. So we've got the topology that we drew. We're grouping here just by the ASN that we did set in the original file. So that's what the different blocks are showing. So we can see that there's a few ASs set up. We've got the green. So the green on the interfaces, which are the GE04, 02, etc. on the link, that bit there is showing that we've got a response back from the VIRL simulation engine saying that that interface is set to active. If we change that to being shut down, then that would change color. And then the green on the nodes where it says the node name in like OSV4, etc. in green, that shows that it's both active and that it's responding to a ping. So what would happen is when we launch a topology, I'm not going to do that here because that can take a while, that it would first start off in like an orange or a red state, and then it would go to black once it's active, and then once they go to green, we'd see a message coming up in our log, and we would also see it go green here, and that means that it's ready for us to log into. And then we'll run through some of the other features. So the simulation log piece really shows exactly what's going on for all the bits. So if something's sort of unsure when to check what's happening, the log's usually got some information on it. So we can see here that the first 5 or 6 entries are saying node X is reachable. So what that means is that that node started responding to ping. And once you launch the topology, the nodes will all start up at slightly different speeds. So some might be 30 seconds or a minute slower than another one. So we'll see once it starts responding, it will show up there. Now what we're also doing is once we see in the live visualization that a node has changed status from active, which means it's booting up, taking a config, to reachable, when it does that state transition, we then log into the device and grab its IP addresses. So we'll run the collection command. We can see the IP addresses have come back here. So what that allows us to do is then to process the IP addresses out of the that response, and we can display them here. So we can see here that the IP address, the third entry down for the node and the second entry for the interface, we can see the IP address there is what we've got from this previous piece where it shows us the IP address table. We've now parsed that out, and we can use that in things like when we run traceroute and get the IP addresses back, we know which IP has come from where. And then we've also got the MAC address. So that's showing us that information from the network, and it's also giving us something we can use to reverse map. Now this has come directly from the show command. So if we change that IP address, we could run that again and get it updated. So you don't need to have used the Autonetkit IP addressing. We're collecting this information live from the network. We can also see, once again, that node and interface status. There's 3 diagrams here. We can see on the node status on that tooltip, which you just get by hovering on the node, the SIM status is set to active, which means it's both reachable and set and active in OpenStack, and that's green on the node. In the middle one, we're just showing the nodes and interfaces zoomed in, so we can see there's a couple of interfaces that are red, which means they've been shut down. And then over on the right-hand side, we can see if we hover over a node, that the SIM status for that node on the first line is showing that its SIM status is false, which means that it's not running. But usually just visually seeing if it's green or red will indicate whether things are up or down. That's a quick way to see basically for the whole network in a second or so what's up and running and what's down. And that can be quite useful once you're playing around and seeing how the network routing or whatever behavior changes as you take interfaces up and down. So in terms of bringing interfaces up and down, you've got the context-sensitive menu. So when you click on a node, you'll get this menu here. The first entry is shut down node. If you click that, it will ask to confirm it because it is a reasonably time-consuming operation. Send that through to the simulation engine, asking it to shut it down. And then once it starts shutting down, we'll see its color changing. So that will change to red. Similarly, for an interface over on the right-hand side, if you click on the interface, you can click Disable Interface. That will then send through the request to disable it. And then once interface is down, we'll see the status result coming back as being inactive, in which case the interface will switch to red. Then if we want to bring the node or the interface back up, we could just click on it again, and that context-sensitive menu would then say Start Up Node or Enable Interface. I'll show that in the demonstration. We've also got some topology simulation controls. So this is very similar to the user workspace management piece, making the same call where you can extract the configurations. So that will just do the same as extract configurations in user workspace management or VM Maestro, where you can that will log into each device and grab it back. That's just making the REST call, and then shut down the simulation is going to also make that REST call to shut it down. So the aggregated syslog, which we touched on before, this is showing it again for a couple of different devices, and we can see once neighbors and OSPF go up and down, or BGP and things like that, being able to see exactly when those pieces change is really powerful. It's also quite nice if you shut down an interface, you will then see once OSPF or whatever you've got syslog set up for changes, so you know then that the routings are changed or the routings reconverged, and you can then run a trace route. So it's quite quite useful for double checking that topology changes have propagated through the network. You can also run CLI commands. So for instance, you can do something like collecting a route table, and then we'll see all the route tables for the devices appearing in the log. So what this one is going to show is a topology visualization piece, which is actually what we originally started out with in the live visualization. Everything else has sort of grown around that as we've added functions. So what we can do is if we change our protocol overlay from that menu over on the left to OSPF Live, it will switch us to the OSPF Live view from the live data model, so request that from the models piece. And it will also send across the OSPF collection command to each device. And that's what we can see in the raw log here. So it's going to send it to the LXC. It was going to map the OSPF command in the web server to the appropriate collection command for that platform, if it's XR or XE or iOS B. Log into each device, run that command. We can see some of them coming blank because they don't have OSPF neighbors. Anything that it gets a result for, we'll send it through to the processor, which will parse it, turn into the structured data. In further topology, so we'll look at the neighbor ID, look at those IP addresses we collected before, work out which neighbor that actually is, which node it is, and then add a link if appropriate, or remove a link if it's now gone away, update the live models, and then send that through to the browser. So just by switching the overlay in that menu from the physical to the OSPF, waiting a couple of seconds, we will see now the plot of all of the OSPF links in the network. So we can see within each of those groups how that's been set up there. If we do a similar thing for switching to either IBGP or EBGP, because it's the same command, it will then also send that collection command for IBGP summary, process it in further topology, update the models, and then send that back. So we can switch just to the IBGP view, and we'll see the IBGP peerings plotted a couple of seconds later. And similarly, if we then switch to the EBGP view, we'll see the EBGP peerings. So if we go back here, IBGP, of course, is just within the network. We've just got a full mesh set up here. And then EBGP is going to be between each of those AS networks. So that all comes automatically just by changing the overlay. If we want to run it again, if we've changed the topology, you can just go actions and then run BGP or OSPF or whatever command. And that will then send the collection command and then trigger the rest of the workflow to automatically get updated. One of the other things that we've got is the visual trace route. So what you can do is under that context-sensitive menu, either for a node or for an interface, you can say trace from, which is going to set that as being the source. And then click another one and choose trace to, which is going to set that as a destination. And then what's going to happen is that's going to send the appropriate trace command by reverse mapping those IPs that we collected. Send that across to the server. The web server is going to map that to the actual trace command. Send that to the management LXC, run the command, get the result to the processor. It's going to process that into a path and then send the result back. So we can see just by clicking from that source to the destination, we've run the command. We can see the result coming up in the bottom of this raw log here. And we've got 6 hops. And then we've plotted the path automatically. So we know, based on those IPs we collected, which node it is at each hop, based on the interface IPs. We can then plot a path through the network. And then if we hover over that trace route, we will then see the each of those hops along the way. And so what we could do is something like combining all those pieces together, and this is where it becomes really powerful, is we could do something like shutting down an interface. I've shut down a couple in this example here. What we would then see is if we look at syslog, we'd see the interfaces go down, the OSPF or IBGP sessions go down appropriately, and then we can run traceroute again. We'll see the router's taken a different, the network's taken a different path to have that route through the network. So once you start putting these various pieces together, like shutting down nodes and interfaces, being able to log in and change them, and then running a collection command as well as the syslog, each of those pieces together makes a really powerful platform to quickly experiment and try out various scenarios on the network, or just learn about how networking works by being able to quickly visualize how changes occur. So I'll do a quick demonstration. I'm not sure how we're going for time, actually. But all these videos, well, the demonstration videos are up on YouTube, on the VIRL channel there.
We got time.
Okay, excellent. So hopefully the visualizations are showing up now. So this is the same topology that we were showing earlier. what we can do is something like trace route. We can just click trace from, and then trace to. Let's see if it runs. Let's reload this one. And I've killed it. Excellent. Second try. All right. So if we trace from a node, so what we can see here is the all the status has changed a couple of seconds later when the topology came up. So once we got the response back from the simulation engine, we saw the interfaces go from being black, which means we didn't have the state, to being red or green appropriately, and also the interface statuses. We go into the log here, we can see that each of the nodes have come up as reachable because they've already been booted up. We haven't had to see them go from inactive or suspended or whatever terminated state it started off in, through to booting, through to active, through to reachable. They've started off in reachable. We've got the LXC data, which we've got up here, and the server load. And now that each of these are reachable, we then know to log into them and grab what the IP addresses are. So we can see now by hovering over each of these pieces, we'll get the IP address and we'll get the MAC address. So now if we'll try again the trace route from this one to this one here, we can see it plotted across the network. And then by changing the path, so if we do something like just clear the path, if we plot from here to here, we'll say to take that path. So what we can do is set up syslog, which is going to log into each device here and just point the syslog back at the LXC, which is the LXC IP address here. And now in syslog, we can see that we've logged into each router and set it up. So we can do something now, to zoom in a little bit. If we go to here and enable the interface, we now see our message saying that we've requested the interface to come up. We now see from iOS v4 that the interface line protocol up down has said that the interface is up. And we also now see iOS v3, which is the other end of the link, saying that it can now see iOS v4 on OSPF. It's gone from loading to full. So that's where it becomes quite powerful to be able to see the other points responding to a change event. So theoretically, if we trace from this one here to this one here, we would expect it to take the direct path rather than the previous path where it went up and around. So if we hover over it, we can now see it's taken that direct path with the interface, ingressing interface is highlighted, or this one here. So we'll just close that one there. So if we want to have a look at the OSPF topology, it's going to be slightly different to the diagrams we would expect because this interface here has been shut down and this interface here has been shut down. But I brought this other one back up. So we would expect it to be pretty much what I showed in the slide deck, but with those two missing. And we can see that here. So we'll just get rid of those trace route paths. So we can see here we've got mapping following the physical. Here we're not getting those interfaces because we shut down this link, and similarly here we're not seeing those because that was shut down. If we switch to IBGP, we should expect to see the same as what was shown in the slide deck because IBGP is just setting up a connection between them regardless of what underlay IGP it takes. So if we do that here, we're going to see a link across here because for the iOS v7 to connect to 6, it's going to go right down and around, and that will be a legitimate established path. And we can see that through here. And then eBGP is going to be just the eBGP connections there. Let's just trimmed out that one. So that's showing the basic overview of what we can do with bringing interfaces up and down. We can enable this one here, showing the node status, the trace route, and then the various overlays. And if we want to do other bits and pieces, we can collect information. So we don't do anything actively parsing it, but we can do something like collecting ARP, which is what we use for the MAC addresses, or we could do something like connecting the running config, which takes slightly longer to log into each device, but we can see we've still got that back for each one. The running config's probably a little bit too much data to scroll through in a log file. So we could look at other ways of doing that, or something like the route table, and we can now see all our routes that come through. And of course, these routes are going to be changing as we modify the network, which is once again why the syslog is something I use all the time to be able to see once that change event is propagated to the various devices propagated through. So that's that. But there's a couple of features there that will be coming out in the newer version of the live visualization in the next edition of VIRL, but most of the features are already there today if you go through any of those access methods we covered, whether it's via Maestro or user workspace management or directly. And more information and feature requests, you can just go onto the YouTube channel. It's got some nice demonstrations, or on the just go through the website to the VIRL discussion piece, and it's got some really useful information there. And we'd love to hear feedback about what other commands or information or anything else people are interested in getting. And so that's a quick summary. I think I've run over my time, so I'll hand it back to Valerie. Thank you.
Thank you, Simon. So yeah, like I mentioned in the chat, everyone, we don't usually get to have Simon on the call because he's on a completely different time zone, joining us from Australia right now, actually. So definitely ask your questions in the Q&A while we got him here. And I will hand it off to Tom, who will take us on our next topic.
Thanks, Valerie. Let me share a couple apps here. Okay, so the next part we're going to talk about a new feature, I guess a new setting we're exposing in the user workspace management web app for RAM and CPU overcommit values. So let me get via Maestro up here, and we can take a quick look at what this feature is and why you might want to use it. Here we go. Okay. So for this example, I'm just going to I'm pointed at a VIRL backend here. I'm going to try to launch this simulation, which has 3 iOS XR-V nodes in it. So I've already drawn this, configured it, it's kind of ready to launch. I click launch, and this is going to send it to the backend and try to spin up the simulation. And the error message I'm getting here, if we read it, says that the simulation that I'm trying to launch, there's not sufficient memory on the back end available for running a simulation of that size. So it's saying I need about 9 gigabytes of RAM. I only have 6.5 available. So we're going to take a quick look at, ways to tweak that setting and where those numbers are coming from. So if I look at the back end, at the UWM, well, first we'll look at this this VM itself. So this backend that I'm using has allocated to it, meant to have this up and open, has allocated 4 virtual CPUs and 8 gigabytes of RAM for this VM. Nope. Sorry. This one. There we go. So this is similar to if you have, a decent MacBook Pro or something, you might run a simulation with, or run the VIRL VM with this sort of setting with 8 gig of RAM for the VIRL VM itself and maybe 4 cores. But even though I have about 8 gigs of RAM allocated to the VIRL VM, just the Linux operating system, the VIRL web services, the visualization pieces, that all has a certain amount of overhead. So even just running no simulations right now, we can see on the UWM overview page that just VIRL sitting there is already chewing up about 3.5 gigs of RAM. So the other 4 gigs is available for running simulations. But of course, here we saw in via Maestro that it was talking about 6.5 gigabytes. And the reason it's doing that is that instead of just limiting us to the exact RAM that the backend has available, let's see, we are going to system configuration. If we look under now in the upcoming release, system configuration resources, this is not in release code yet, but it'll be coming in November. We have this RAM overcommit value. So basically this is saying, based on your actual RAM on your machine available for running simulations, here's the overcommit value. So sort of multiply that value by 1.6, whatever much RAM you have, and that's the amount of RAM that we're going to give to simulations. So I'm going to just tweak this value for a minute. In the new UWM, we'll have the sort of preview about what changes we're about to set. I can apply those changes. And now if I go back to this simulation and try to launch him, now that simulation is launching up, right? So just that setting modified sort of the VIRL's calculation about how much RAM we have available for simulations. And so look at this for a second. In the VIRL sort of architecture, there you have your user interface. When you launch that simulation, we're handing the topology back to the VIRL backend, whether that's a virtual machine or a dedicated machine, however you have that installed. And the simulation goes down to the topology goes down into the simulation engine service, which is responsible for launching that. But at the end of the day, we launch those simulations on top of OpenStack and Linux KVM on the VIRL backend. And that virtualization layer, the OpenStack and Linux KVM, virtualize your hardware so that you're running these virtual machines, and it's using the real hardware, but presenting that virtual layer, and it can oversubscribe that both the CPU and the memory resources. So instead of just saying I only have 4 gigabytes of RAM left and 4 cores of CPU, and I'm limited to those values, we can say, instead we're going to say, set the overcommit value to 2, so I'm permitting, the virtual machines the routing virtual machines to take up to 8 gigs of RAM. And that works by, paging out, using some duplicate page sharing. It can swap out some memory. The CPUs just get time sliced. So if we look over here at the launching simulation now, that simulation is up, and we should be able to get, the simulation is partially up. It's coming into the configuration mode. XR takes a little while to come up and run its configs. But this simulation now is booting on the back end. Now, it's important to understand that overcommit value. Let me go back to the UWM. So again, it's under the UWM VIRL server system configuration under the resources tab. So right now I've set it to 2.3, and at this point that means sort of that 4 gig times about 2.3. That gives me something like 9.5 gigs of RAM. I'm saying the VIRL simulations are permitted to use. Now these values aren't magic. They're not creating any more hardware resources than we already have. So that means that if your simulations are already memory constrained, resource constrained on the memory side, adding a higher overcommit value is not going to make anything perform better. It's going to actually make things worse. But if you're running a simulation that's running and performing very well, the virtual machines are responsive, things seems to be functioning properly, and you'd like to add just like 1 more node or 2 more nodes, just by tweaking that overcommit value a little bit, you might be able to add those in without losing too much performance. At some point, these values will completely degrade performance. The feature is not experimental in the sense that we're not sure if it works. I mean, it works how it's supposed to. It's leveraging that overcommit value, but it's experimental in the sense that once you start modifying these from the default values, all bets are off. If you set these values too high, you can make your VIRL backend sort of grind to a halt. So we'd recommend changing them very slowly. The values that we come with default, the default value is a 1.6 here. Those default values 1.6 and 3 we think are reasonable for basically all the virtual machines that we ship with, all the router VMs that we ship with by default. But depending upon what your topologies are that you're trying to run, what virtual machines you're trying to run, and which what you're trying to do with those virtual machines, it could be safe to run higher values like like for this example where I'm running 2.3. So let's see. Right. So like I said, we're now able to get into this instance. It's performing fine. And XRV seems to be fairly fine with having a slightly higher overcommit. It also helps if I'm running simulations that are largely the same node type, basically the same virtual machine image. That'll help with some of the RAM overcommit. It's able to share a little bit more among the nodes. If I'm doing just some light protocol configuration, possibly not a big problem. If I'm pushing lots of routes, it might be more of an issue. It's really something that you have to kind of play with and experiment with. But like I said, it's sort of training wheels are off at this point. Tweak the values very slowly as you play with it to see what does and doesn't work for you. So I'm going to stop this simulation and mention a couple other things that we might want to use here. While that stops, I'm just going to mention where that 9 gigabytes came from. So I have a topology here that has 3 iOS XRV instances. That 9 gigabytes that VIRL said I required is coming from, each of these nodes here is an iOS XRV node. If we look in the properties in VM Maestro, we see that it has an iOS XRV subtype and a blank VM image and flavor. So each of these virtual machines comes up with a specific virtual machine image, and from the OpenStack side, everything gets a flavor. You don't have to fill those in by default. If you don't, we'll just use the matching images and flavors in the back end. So we have an iOS XRV there. We have some sort of VM image on the images side, and then we have a iOS XRV flavor in the flavors. So this is the iOS XRV flavor. And as you can see, the iOS XRV flavor is set to what we expect it to require. It's 3 gigabytes of RAM. So when I'm trying to launch these topologies with the new image, the iOS XRV, each instance requires about 3 gigs of RAM. So with 3 of them, that's where that 9 gigabyte number came from. If I then go here and try to add, say, a server to this, this is the sort of thing I was talking about, where it's like, okay, I'm good. That was kind of running fine. Let me add one more device. I'm going to run it through Autonetkit to configure that server node for me. And then if I try to launch that, whoops, oh, that actually worked. Okay. Depending upon exactly how much free memory I have, this can get right to the edge of maybe launching, maybe not. And as I get to that edge, again, if the current simulation is running fine, I can come back in here to the VIRL server system configuration and go to those overcommit values. As soon as I get a failure, I can switch over to this, make some change here, change it like to 2.5 or something, apply that change. There's no need to restart or reset anything. It's sort of evaluated every single time you launch. So now that new resource is set, if I had if I have a simulation that was working fine, and when I added one more node to that simulation or tried to run another topology that was, just one more node in addition, then if that one failed, just tweaking this value by, 0.1, 0.2, I can then possibly run that one extra node and then, verify, okay, the simulation's still kind of running okay. It's stressing out my hardware a little bit more, but it's still getting me acceptable performance to run that. The other place that you really might see this, we've had some people report after, let me go to the overview. Like I said, there's some sort of resting state, memory that's consumed by VIRL just by the operating system itself or by the database system software that we use. So it's possible that when you boot up VIRL for the first time that you can launch a topology and you run that simulation, you work with it for a while, you shut it down, and then you come back from lunch, you try to start that same exact topology again without restarting the VIRL backend, and sometimes that will fail. And the reason we've seen that fail is that, the initial launch was so close to your memory limit that, once you launch and come back, there's a little bit more memory pinned by the database processes or something, and then that's now squeezing it, just a little bit over the threshold. And that's a very good case for saying, okay, well, if the if the topology launched fine, when I came up with a clean system and I shut it down, I tried to launch it again, and now it's failing, it's got to be just right at the edge, and just bumping up that RAM overcommit by 0.1 or 0.2 will probably get you the ability to just launch it consistently without having to clear anything or restart the VIRL backend. So we're putting this in there. It's always been in there as part of the OpenStack backend. This overcommit value. It's sort of a OpenStack feature itself. And there's some additional documentation in the flyover tooltips here. I've talked mostly about the RAM overcommit. You get a similar thing from the CPU overcommit. Right now we set that by default to 3, so we kind of time share the CPUs by 3, by a factor of 3, and you can tweak that value. Depending upon the router virtual machine, this can cause problems. But again, it's one of those values that you can tweak a little bit if you're getting, if you have a ton of RAM on your machine but not so many CPU cores, you might actually hit the CPU limit before you hit the RAM limit. And in that case, you'd probably be tweaking, the CPU limit the same way, sort of set it to 3.2 or 3.5 and see if that runs still acceptably, but with getting a few more nodes on your system. And again, like I said, this value's always been there. We just haven't exposed it for you to tweak yourself. The defaults should be fine. If you want to get back to the defaults, you can just, we'll ignore the values you set there. You just click the defaults, click Apply Change, and this will get your VIRL system back to the out of the box defaults for that feature. And then if you find values that seem to work pretty well, or you find ones that are particularly sensitive, like XRV is very happy with a higher RAM overcommit, but CSR 1000V isn't, that would be great information to share with all the other users on the forum, especially when you're talking about, say, third-party VMs that we don't track ourselves. So I think that's it from me. I'm going to hand back over to Valerie. Like I said, you will see that feature coming in the next release of VIRL, which I think we expect in November sometime.
All right, thank you, Tom. Let me steal the ball back. Yep, like Tom mentioned, this is something you're going to be seeing in the next release, where we're trying to incorporate bits and pieces of those sneak peeks in each of our webinars, so you guys can see what's upcoming and get excited about them. Okay, so coming to the end of the webinar, we have our special announcement of today. So as many of you know, it's been a very popular request that people, their users can perform simulations on VIRL with more than 15 Cisco nodes, and a lot of discussions around the topic. And we've been collecting a lot of feedback through Cisco Live, a lot of discussions on the community forum, and someone even started a petition to have 500 people sign up to have VIRL nodes raise the node limit, and we do appreciate the importance you put on our product. After all of those discussions, we are now excited to announce that we will be raising the node limit from 15 to 20 on November 1st. So as long as you have a working license, your node limit will be raised automatically. It will be free of any charges. If you purchase the licenses starting November 1st or afterwards, your node limit will start at 20 automatically. And for those of you that have a even larger need for a number of nodes, we are having a 30-node product that's going to be released on November 1st. It will be available to purchase on our website, virl.cisco.com. And so make sure to check there for product details. If you already have a license but you want to use a 30-node version, you can choose to upgrade your license to a 30-node, and you will actually receive credit on your old licenses depending on how many months you have left on your original subscription. You can upgrade your licenses through your account where you downloaded the license key, which I have showing on the screen here. I will actually post those links to chat right now as well. And starting also on November 1st, you will be able to renew your licenses. All you need to do is log into the account, like I mentioned earlier, and you will see when your license expires, and then you can choose the ones you want to renew. and just check out with those. And if you renew before the subscription ends, you can get 10% off of your next year. So that would be 10% off of $199.99, and you can get it at $179.99 for your next year. And if you want to keep VIRL for multiple years and you don't want to keep renewing it every year, you can just have it done once and for all. Just renew it for multiple years, or for however many years you would like to keep VIRL for. So let me post those links, including our website and your accounts, to the chat room right now. That's it for our announcement today. And as I mentioned, these are some very exciting news for us, and we're happy to keep bringing our users what you are asking for and keep making VIRL a better product with each release. So give us a shout out if you end up upgrading or purchasing the 30-node product, and make sure that at the end of this webinar you fill out the survey that we send out to get some feedbacks, and we do read each and every comment that you guys send in. And we'll see you in the November webinar. Thank you, guys.